Hello, my name is Jeremiah Tirizalde, and today I'll be presenting the algorithm design techniques. And the three algorithms I'll be discussing today is going to be divide and conquer, dynamic programming, and greedy algorithm. So we'll start with greedy algorithm. So in a nutshell, what is a greedy algorithm? A greedy algorithm is a problem-solving approach where decisions are made step by step, choosing the most beneficial option available at that moment. The goal is to reach an optimal or near optimal solution by always making the locally optimal choice. It doesn't go back, it doesn't rethink its choices, it simply makes the best decision it can make at every step of the way. So what are the key characteristics of a greedy algorithm to work effectively? There are two key characteristics. Number one is the greedy choice property. It is about making a locally optimal choice that leads to a globally optimal solution, right? Number two is the optimal substructure. Over here, the problem can be broken down into smaller subproblems, and solve them optimally solves the larger problem. We'll have real-world examples for both characteristics later on, but if either of these properties does not hold, a greedy algorithm might not work correctly. And if we go back to the key characteristics of a greedy algorithm, we have to keep in mind that there's also a greedy choice property. Now, what exactly is a greedy choice property? Well, this property means that a solution can be constructed by making a series of locally optimal choices. That is, at every step, you make the best decision available without considering the future consequences. And these choices will ultimately lead to the globally optimal solution. So let's go with a real-world example, okay? Let's say you have a change for 6 pesos and you have to find the fewest number of coins to have a change for this number of pesos, right? But the coins you have is only 1, 3, and 4. The greedy strategy says that you always have to pick the largest coin that doesn't exceed the remaining amount. The largest number among the 3 coins is 4. Then you're gonna pick there's 2 remaining coins, which is 2 pesos, and the only way to cover that is by doubling the 1 peso coins. So that ultimately leads to 3 coins. So in reality, the lowest amount of coins that you can use to have a change for 6 pesos is actually 2 threes, which is just 2 amount of coins, while the other one was 3 coins, right? The greedy algorithm doesn't work in this use case, but it can work for another coin system, and that is the US coin system. If you look at the US coin system, there's a 1 peso, 5 pesos, 10 pesos, and 25 pesos. So let's go back to our example with 6 pesos. If you use the greatest number, which is 5, and pick the remaining, which is 1, then you ultimately only need 2 coins for the change of 6 pesos. As for earlier, it had to result to 3 by using the greedy algorithm. However, in this case, in the US system, US coin system, exactly, it can work. So over here, we're going to figure out how a greedy algorithm works in a coding setting, okay? So here we're going to define a function. We're going to create a function that will accept one parameter, which is going to be activities. And over here, we're going to find a way to sort activities based on the errand times, right? So here, this basically means that we're going to be sorting by the second element of each tuple, right? Tuple. And here we created 2 empty variables that we're going to fill in and use as a basis for our function. And this will be empty because we're going to be adding on the selected activities that will fit the schedule, right? We're trying to fit the most out of our schedule, right? And the last end time is going to be 0, assuming that there is no selected activity. So over here, we're going to create a loop that goes through each activity in the array of activities over here. So start will be the start of the schedule. So assuming that the schedule starts at 1 p.m. up until 9 p.m., right? So start will be the first and the end will be the second for each activity. So if the start of each activity is greater than or equal to the last end time, 0, because again, assuming there's no activity selected yet, it's going to be the basis or the starting endpoint. It's going to add to the activity over here. And the last end time will be equivalent to the end of the first schedule, which is 4, right? So it's going to keep doing that. So let's try to simulate this code over here. So for each activity and activities, we're going to get this. So we're going to start here. So because this is equivalent to 0, we're going to ask if start is equivalent or greater than the last end time, 0. Start is this one, of course, the first one. Then we can append the whole thing in the schedule. Because 4 is greater than 0, we can add this whole thing over here. This will be the first available subject that we can have in our activities. Now, because this is true, we will then update the last end time to the end time schedule of the first activity, which is 4. So this will then become 4. We're going to go to the next variable in our array, and we're going to calculate if the start, number 3, is greater than or equal to the last end time, remember 4, then it will add to the activity. But 3 is not greater than 4, so it will ignore this and it will not be added to the, the last end time will not be updated. So x. So the last end time is still 4. We're going to find the next one right here. We're going to go to the next variable in our array, right? Now let's go back. If the start is greater than or equal to the last end time, then we can add it. But is 0 greater than or equal to 4? It's not the case at all. So we'll go to the next one, which is 5, 7. If the start, number 5, is greater than or equal to the last end time, 4, then we can add it, right? Because 5 is greater than 4. So it will get this and add it to the selected. So let's check. But again, since it's true, we have to update the last end time to 7. So this will become 7. So once everything's said and done, let's try running this whole code. And let's see if this is correct. So the second array should be 1, 5, 1, 4, 5, 7, and 8, 9. The time complexity for this greedy algorithm is big O of n log n. This is because Python uses a time sort or sorting, which is a hybrid sorting algorithm with a time complexity of O n log n in the average and worst cases. So let's move on to our next topic, which is going to be divide and conquer. So divide and conquer works by basically breaking down a big problem into smaller sub-problems of the same type and solving them recursively, and then combining their solutions to solve a bigger problem, or the original problem. And there are 3 simple step patterns that this divide and conquer algorithm works. So number 1 is divide, where we split the problems into smaller sub-problems, and we conquer by solving each sub-problem, and it's often done recursively. And the final step is to combine, where we merge all of the solutions of the sub-problems into one final answer. Now, this method is often used for bigger problems that would otherwise be inefficient or very complex to solve directly. Now, so that we can understand it better, let's try using a real-world example for this case. How about cutting a pizza fairly, for example? Imagine you're hosting a party and you want to cut a large slice of pizza for 8 people instead of measuring and slicing every 45 degrees from scratch. So here's what you do. You divide and cut the pizza in half. And now you conquer by cutting each of the halves into 2 slices, and now you're gonna have 4 pizzas. And with those 4 pizzas, you cut them again individually until you have 8 slices altogether. And in the end, you solve the bigger problem, or the original problem, where you need to serve 8 people equally and individually. So there are 3 major details of a DNC, or a divide and conquer algorithm. So number 1 is optimal substructure, where the solution to the whole problem depends on the solutions of the smaller subproblem. The next one is recursion, where the function calls itself on each of the subproblems. And finally, the master's theorem, where it analyzes the running time of the divide and conquer algorithms. So in this example, we're going to be using merge sort algorithm for our example for the divide and conquer. So we'll break down the list into smaller parts and sort them individually, and then merge them back together into one sorted list. So let's dive into this code. So here we're gonna figure out if the list is only empty or only has one item. Then we can assume that this list is already sorted, and we can return it as it is. So if the length of the array is less than or equal to 1, then we can return it. Here on the other end is where we divide the list into halves, and then we recursively call merge sort in each half, merge sort being this function right here. This continues until we reach the list of size 1. So left half is going to be divided here. A is equivalent to merge sort array mid, and right is going to be yours. So it's going to be divided into 2 halves, and we return merge left and right, right? So here is where we merge, is the merging function, right? This function will merge the 2 sorted lists as left and right in this parameters right here. We prepare an empty list to store the results and use the 2 pointers I and j to track the positions into the 2 lists, right? So while I is less than the length of left and j is less than the length of right, then we'll do this. If this is true, then if the left half of the list I is less than the right half of j, then we're gonna sort the array and append it to the left of I So I plus equals 1. So it's going to go through that. So we're going to go through both list and compare elements, and the smaller values added to the sorted list. We move that pointer forward. This ensures that the result stays sorted, right? So we're going to add the leftover elements right here. If there are any leftover elements on the list, we add them to the result. We use extend to efficiently add the rest of the items. So we're going to use this example of this unsorted list, and we test our merge with the unsorted list, right? So we have 38, 27, 43, 3, 9, 82, and 10. So if you run this code, it should be sorted from least. Now when we get the complexity of the code we used earlier for merge sort, the time complexity would be big O of n log n. Now why? Because the merge sort uses a divide step. So basically at each level the array is split in half, and the number of levels in the recursion tree is log squared n. And in the merge step, at each level of every element is involved a merging process. So the total work per level would be big O of n. So when we combine it all together, the overall work across all levels would be big O of n log n. So all in all, divide and conquer is a fundamental strategy that breaks a problem down, conquers each of the pieces, and combines the results. It's everywhere, from searching names in the book and how to use computers to sort files, and when it's used right, it makes solving complex problems elegant and efficient. So our final topic for today will be about dynamic programming. So what is dynamic programming? So dynamic programming, or DP in short, is a technique used to solve problems by breaking them down into smaller overlapping subproblems and storing their result to avoid redundant calculations. In simpler terms, it's to solve small parts once and reuse the results instead of recalculating them over and over and over again. Now, how does DP work? Dynamic programming is based on two principles, and one is optimal substructure, very similar, or if not exactly similar, to the one in divide and conquer, and the other one is going to be overlapping subproblems. It's the same subproblems repeat multiple times. Instead of solving them again and again, we store the result and use a technique called memoization, or a table tabulation. Now, what's a real-world example for a dynamic programming problem? So let's say you're a cashier and a customer needs 27 pesos in change, and you have an unlimited supply of coins in the following denominations: 1 peso, 5 pesos, and 10 pesos. Now, what is the minimum number of coins you can give to total 27 pesos? Now, here is why dynamic program will be useful. Because of this, you can break down this problem into smaller subproblems, right? Now, let's figure out what's the best or smallest number of coins ways to make 1 peso, 2 peso, 3 pesos, and so on up until 27 pesos. You build up these solutions and the bottom up, reusing the answers to smaller amounts to calculate the answer for the larger ones. So today we're going to give an example for a code for dynamic programming, and here we're going to find the nth term, or let's say we're going to indicate the number here. We're going to find the 10th term for the Fibonacci sequence. So here we just simply define the function called Fibonacci sequence, or Fibonacci DP, and it's going to take an integer or a parameter that's scan, and the goal is to find the nth Fibonacci number, right? So over here we're going to figure out if this line here, if n is less than or equal to 1, then we return n, because if n is 0, we just return 0, or if n is 1, we return 1, because there's no need to compute any further. We're going to create a list called fib of size n plus 1 and initialize with all zeros. So this will store the Fibonacci's numbers from fib 0 to fib n, right? So from the starting all the way to the nth term, which is 10, right? So here we're gonna have a loop, right, for I in range 2 and n plus 1, right? So the core formula here is the current Fibonacci number and sum of the two before it, right? So example, fib 5 is equivalent to fib 4 plus fib 3, right? It's gonna happen so on and so forth until it reaches the 10th term. So if you run this code, it should be 55. And the previous number before that, let's figure out if it's gonna be working here. 34. When we look at the code earlier for a Fibonacci sequence, the time complexity of that would be big O of. Now, why would it be big O of n? So this is because the loop runs from I is equivalent to 2 to n, so it iterates n minus 1 times. That's linear time, right? Each iteration does a constant time operation where Fibonacci I is equivalent to Fibonacci minus I minus 1 plus Fibonacci I minus 2. So the total work is equivalent to the big O of n steps times big O of 1 work per step, which is going to be equivalent to big O of n. So thank you for listening. This has been Jeremiah Rizalde presenting the 3 algorithm types: divide and conquer, greedy algorithm, and dynamic programming. Thank you.